Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Series, Author Series. And I'm super happy to have Rachel Bruch with us today. Hey, Rachel.
Hello. Nice to be with you.
Nice to meet you. How are you today?
Great. Good. End of the week. Really nice.
And where are you located, Rachel?
At the moment, I'm in Rehovot, which is some sort of suburb area near Tel Aviv in Israel.
Ah, okay. Awesome. I believe you have the honor of being the first author video from Israel. So that's fantastic. Let's see, it is May 27th and I'm here in Phoenix, and the power switch for summer has not yet been touched. We're getting close, maybe another week or so, we'll start getting up into the 40, 43 Cs. But today it's going to be fairly reasonable at about 35, 36 C or so. So has summer hit in Israel?
Summer never ends.
Summer never ends. Well, you are a lot closer to the equator, so there you go.
we had a pretty nice, not too hard winter. So now it's getting back to hot, but it's like so I don't know Fahrenheit, so it's like 25, 30 degrees.
Oh,
so
that's very pleasant.
So it's really nice. It's like how is it like? How is it now in Arizona? Again,
it will get very hot in the summer. We'll get up to 43 C. 43, 44 C, it gets toasty. On the other hand, in the winter, it's very pleasant. January, February, it's very pleasant in Phoenix. 30 C, 25 C, something like that. So we get a lot of people coming in, snowbirds coming into Phoenix for the very mild winters that we have in the States. So it's very cool. That is a very awesome image over your right shoulder. What is that? So it's an adaptive optics, and what's the observatory there?
It is the VLT.
Oh, okay.
Being very happy because I think it's one of the most beautiful posters that ESO has in their shop in Munich. So
that is lovely. Very cool.
Also, you can see the large Magellanic clouds. And
yeah,
it's
yeah.
really
very nice.
Can't pick my computer, but it's really pretty.
Have you used the VLT? Have you used it?
No.
Okay.
One day soon. I'm starting the career. So.
There we go. So let me just ask, what's your position there? Are you a postdoc?
No, I'm a PhD student.
Awesome. Very cool.
So I'm a little bit after what we call the mid, which is just the middle of the PhD, but we have an exam for that.
Okay.
And I'm supposed to end in a year and a half. So I'm
cool.
It's starting to get very, very interesting now. It's a bit less confused, more, and then paper is out. So it's like,
yeah, this one is out. So in general, what do you like to do for research?
Well, so at the moment, my PhD is clearly focusing on trends in science and supernovae, and especially the early time behavior of supernovae, and triggering as fast as possible follow-up research, resources to have the best set of data possible at early time for a largest amount of supernovae we can gather. And what we're interested in is trying to understand how massive stars are ending their lives, and is there something that could let us know before that they're about to die? So there are several areas of research about this, and one research that we have here is the precursor search, to look for little bleeps before the big boom.
Yes.
But in my case, it's more during the big boom and the early big boom. Is there something that can tell us about the close environment of the star as it's exploding, and is it different? Is it like are there common patterns? Are there not common patterns? And it's a sort of something that has been worked on in the past, but now with the facilities that we're having, we're opening up really incredible and crazy research.
Very nice, very nice. And that is going to bring us to this very lovely APJ article A large fraction of hydrogen-rich supernovae progenitors experience elevated mass loss shortly prior to explosion. And Rachel, take us away.
Thank you. So I kind of want to introduce a little bit ZTF, which is the Zwicky Transit Facility, although I'm pretty sure that it was already talked about before, since we're entering the second phase of the survey.
Yes.
But the main idea is that we're having a constant nightly, multiple times per night measurements of the northern sky in G-band, R-band, and I-band.
Nice.
So we have an incredible cadence, and we have a really nice multi-band, optical multi-band information, which is coming to us. And it's allowing for finding very young and fast transients. And by young, I mean we can be, in the case of supernovae, we can be very close to explosion time. So just like wanted to give it how much, a little bit of context of how much ZTF is changing a little bit the game before, because there was PTF before,
right?
Which had also a good cadence, but it was only in our band, and the constraints on explosion time were not as good as we're getting now. So that's a great thing. So the one thing that that this paper is tackling is trying to give an answer on how common is it that a progenitor of a supernova, and especially of a core collapse supernova, would be embedded in a circumstellar material.
Okay.
So by circumstellar material, in general, like just like something which is confined to 10 to the 15 centimeters, something like this, from the star.
Mm-hmm.
And so we're not answering what is exactly the mechanism, but we're trying to answer, is it common or not? Because well, it's one of the arguments is that most of the models that are being made are considering just a regular massive star that explodes, and it doesn't take into account that it can interact with the circumstellar material. So one argument that I'm just like telling here, and like putting here on the side. So this was sort of a first sanity check with the first year of ZTF. So that was in 2018. We gathered as much as possible core collapse supernovae. We focused on type 2 supernovae, and we used a technique which was coined by Avishai, which is my supervisor. We used a flash spectroscopy technique to look for evidence of circumstellar material or not which would be surrounding the progenitor star before explosion. Just a very rapid, I will go more into details about what is flash ionization features and discuss it a little bit more, but just a very like broad overview is that it's emission lines of highly ionized species like helium-2, carbon-3, nitrogen-3, that you can find in the very early spectrum. So let's say like a few hours from explosion up until a few days. And this is also an open question of what is a few days, but it's less than 15 days. And these emission lines are visible at the beginning, and then they completely disappear, and then the supernova behaves normally, like back to a generic type of 1b, 1c, type 2, etc. So that's like just to give an idea of this technique, and the main channel for the appearance of these lines is that it's coming from the outer layers of the stars are being ejected prior to the explosion. So this means there was a circumstellar material, because there is this interaction of highly ionized species in the early spectrum.
Cool.
So that's it. Like that's a little bit the overview, and now we're getting into the answer. I'm not going to spoil already. I'll tell you at the end.
We'll keep it a mystery. Okay, very cool.
So the idea, so I said core collapse supernovae up until now, but we're actually focusing on type 2 supernovae. So you can go down to figure 1.
up so people can see it. And there we go. Bang.
Thank you.
Okay.
So yeah, so the one thing to take from this plot is that Corpulab supernovae population is mainly dominated by type 2 supernovae. So for a population study, it's better to put everything on, all the chances on your side and just focus on the widest type. So we went for type 2 supernovae. And now there's something, so here it's called RI, it's called like real infant supernovae, because we're trying to have type 2 supernovae which are as close as possible from explosion. Very briefly, like we don't really need to go into details, but our way of working would be that we were scanning every day the feeds of new images that we were getting. Whenever something was going through a set of criteria that we defined earlier, but it's like we would save it and initiate very early follow-up. And then after that, we gathered the entire sample of supernovae gathered in ZTF in the first year, and we looked for tight limits, which is like having a non-detection limit of 2.5 days and having a very significant rise from this non-detection, saying it is expected that type 2 supernovae are very, well, not very, but fast transients. And compared to the cow, it's not as fast, but it's rather fast because we're expecting a magnitude rise of 0.5 magnitude.
Okay.
And so we're focusing on these data. And so among all the type 2 supernovae, we had 6% of them which had these tight limits, so that were caught at least 2.5 days from non-detection. So like the explosion time is within 2.5 days of the first detection. So we constrain this, we create our sample. It was about 28 supernovae that were gathered. So it's from March to December. So it's like less than a year.
Less than a year.
But it's still a rather so it's like for the field, it's a rather impressive number of supernovae caught that young in such a small amount of time, and it's an exciting sample to work with. It was
absolutely.
So then
RI is real infant. I love the acronym RI is real infant.
Now we can go to figure first to figure 3. Yeah, that's just wanted to show that out of the sample we did a good work. We worked well.
There's our 28 and figure 2. Forced photometry. Okay, figure 2. Bang, bang, bang. Okay.
So this is like, obviously we had to reanalyze the light curves that we had, and we performed forced photometry on all the images just to make sure we had all the measurements and with good errors and good estimation over them. And this was for I won't go too much into detail, but it was just like an estimation of the explosion time, and until now we have this like just trying to fit some sort of power law going through the early data. But what is like you can see how rich the data is at very early time. You have like 4 or 5 points in one night in one band, and then you have a very nice constraint of the explosion time for type 2 supernova.
What are the 2 colors of the dots?
Sorry. So the red points are the red band, and the green is the green band.
Of course. Yeah.
Oh yeah, maybe I should say something about the x-axis. It's once we get the first alert, and then we'll go backwards in time. So 0 is the first time we got the alert.
Nice.
And then like you can see like from the first alert we have like a couple of points, more than a couple of points, which is very, very nice to constrain the explosion time.
Very good.
Now we can go to figure 3. I just wanted to show like the type of data we played with. Which,
no, it's great. It's good. Okay, figure 3. Timelines for various, oops, that's a little too big. Okay, let's try there.
So this is a summary of how we performed on the follow-up and constraining these supernovae. So in the x-axis, it's then the y-axis, it's all the supernovae. In the x-axis, it's again the 0th time is the time from the first alert, and the green to the left is the time from the first alert to the non-detection.
Okay.
And the red bars is from the first alert to the obtention of the first spectrum. So there are a couple of cases where we got the first spectrum within less than a day of the first alert. And we have a rather well constrained sample with non-detection limits which go to 2.5 days. Well, it was a requirement, but it's nice to see it on the scale. And most of the sample had the first spectrum within 5 days, which for flash features and flash ionization method is a bit late, but is still very relevant for an early time follow-up. So that was a little bit of summary. The next figure, just very briefly, it's just that we also wanted an estimate on the rise time and on the peak magnitude, just to compare it afterwards when we'll get into the analysis.
Right.
So yes, just also like with this type of data, we had a pretty nice constraint on when is the peak and what's the magnitude of the peak.
The different colored curves, the different models?
Yeah, it's not different models, just that I was randomly changing the lower boundary and the upper boundary to between 0 and 2 days and between 25 and 30 days, so that when I was fitting a polynomial, it was just like let statistics do its job and give me a good estimate with good errors.
Okay, good. I'm with you.
So now we're getting into the meat of the subject.
There we go.
Once we have all of this data and constraints on when is the first spectrum, when is the explosion time, then we just like had a reduced sample with with candidates which had first spectrum within less than 2.5 days from the estimated explosion time. So the reason we were constraining to this is that, as I said earlier, for flash spectroscopy, we need to have rather early spectral, whether early spectra if we want to constrain and see whether or not there were these emission lines, because they can run away in a few days being 3 days, maybe 2 days. So so we just like narrowed the sample to all those that had a very early spectrum, and then we had to choose, we had to analyze, are they flashers? So this is how we call something that a supernova which had a spectrum with emission lines of highly ionized species, a flasher, or is there just a blue continuum saying it is indeed a supernova that exploded and it's very hot? So, but there's no narrow emission lines, so it's not a flasher. So this was the distinction we were doing. And out of these ones, we had in this reduced sample, we had 6 of them. So this is for the peak absolute magnitude. We can go back to the table 2, which has the
here we go in the last column.
Yeah. What's like good. Okay. So in this table, the ones that were showing flash features, and by flash features I mean one precision I have to give is that when we mean flash features, we mean hydrogen, helium-2, and whatever comes after, which is like carbon-3, nitrogen-3, etc.
Okay.
The problem with hydrogen for narrow emission lines is that it could be from the galaxy, and when we have a lower resolution spectrograph, then we can differentiate. So our discrimination emission line was helium-2. So is there helium-2 or is there not helium-2? So that's it. Like the first line in the table delimitates the 2.5 days from estimated explosion time subsample. And in this subsample, we had 6 of them which were showing flash features confirmed, 2 of them which were just like a blue continuum, so not showing flash features, and 2 of them where it's not clear. And by it's not clear, we had like we can go, so now we can go between, like there's a figure 8 and figure 9. First figure 8 and then we'll expand figure 9.
And oh, that's a nice shot. Okay, and right there.
So this is a bit a new thing, because so far flash features, most of the time they were measured in 13fs or Supernova CU. We would see like very like a clear Lorentzian shape emission line with a narrow component on top and a broader base that we attribute to electron scattering. But in some cases, and in these cases, so this was one of the novelty, we're seeing, so first of all, so the first spectrum is from 18DFC. We see this Lorentzian shape, and on top of it, we see like a rather broad elevation from the continuum.
Yes.
And this is something that was also noticed in 18FIF, which had an entire paper about it.
Yes, indeed.
And so these broad structures were also identified in 18EGH and in 18CYG, but they didn't have, well, in the case, especially in the case of 18CYG, they didn't have this narrow component of helium-2. So we're wondering, is this something, but this, by the way, this structure, this narrow structure also disappeared as the supernova was going, like it was developing and evolving. So we're wondering, is this an aftermath of flash features? Maybe it could be that we caught it too late, although it's 1.8 and 1.6 days from estimated explosion time, but still, like, did we catch it too late?
Yeah.
But in this case, like, can we consider it or not as a flash feature? And in figure 9, this is a chi-square test where we made some sort of empirical model of having just a continuum and adding Lorentzian lines. So in the case of DFC, it fits clearly better if you have this broad structure than if you don't have the broad structure, which is the image just under. Like here, if we remove this broad structure, it doesn't fit as well anymore.
I see. Okay, let me back this off just till I see now. Yeah. Gotcha. Yep.
The same for 18FIF. And in the case of CYG and EGH, it was, you could see that there is some sort of broad structure, but when we performed the test, it was not significant enough for the network test. Visually, we can say, there is something, but statistics is clear. Statistics say no. It's not no. It's a maybe, but it's not significant enough to be very discriminative between yes and no. But still, it's a structure which was observed like twice with the examples before, and like it could be something, and it's really interesting to notice it, and also like give a shout out to the community of those who are doing young transient. Like, if you see something like this, please let us know, because it is relevant. So there we go. So now the question that the question that we asked the sample mainly was, how common is it to have flash features? And then how common is it to have a circumstellar material? Because again, like, the idea is that if there are these narrow lines and they appear and then they disappear, and then the supernova is normal, well, normal within the classification that we have today,
Understand.
then what is it? Then it, well, so for us, it's a hint of circumstellar material interaction at early time, which means that we had circumstellar material very close to the star at early time, which means that probably massive stars are undergoing like massive mass loss. Well, they are undergoing. We know that they are undergoing mass loss, but such like to get such interaction means that they're probably undergoing strong mass loss prior to the explosion. And so now, how common is it?
Yeah.
So if we count just on this subsample of 2.5 days, then well, it's 6 out of 10, so it's pretty common.
Yes.
Maybe 8 out of 10 even, so
Sure.
pretty common. But then, okay, we have to temper, and we made Bayesian statistics, and what we end up with is that the lower bound is that 30% of type 2 supernovae, so it's figure 10, sorry. Is that yes, the 30% of supernovae of type 2 are showing these features. Hence, 30% of them are surrounded by the circumstellar material, which is rather confined. The upper bound is saying 83%, but we will be conservative and say that for like certainly 30% are having and are experiencing these mass loss prior to explosion, which is a rather big fraction, and it's confirming things that were mentioned before, and these are like, I don't want to say these are preliminary data, but it was made on a reduced sample of only on less than a year, and one comparison that we can give is that there were in the previous papers on flash ionization features, there were 12 candidates which were showing flash ionization features on the entire PTF sample. Okay. And here in less than a year, we managed to gather 6, maybe 8, actually 9, well, maybe 9, because there is a late flasher, it's not falling in this sample, unfortunately, because it had its first spectrum 4 days from the estimated explosion time, but it's still a relevant component to the picture. So this is mainly the main conclusion of the paper, is that there is a large fraction of massive stars which are undergoing mass loss prior to explosion, and one way to measure it is by using this flash ionization technique, and getting as early as possible data, and seeing the crazy behavior that they have at early time. So, yeah.
So speaking of that, does one ever observe multiple flashers? In other words, does one event have a flash spectroscopy, and then N days later it goes through it again as though there were separated shells of material, and each one induces some flash spectroscopy? It's just a crazy question. I'm just going.
So there is something that not that we encountered, but that I encountered as a PhD student who's discovering and like understanding and gathering a lot of knowledge and data, is that there was one where it had interaction at early time with a confined shell, and then when we check in the nebular phase, there's a very narrow line which says that there's some interaction still going, but probably with like expelled shells from a long time ago.
Right.
So it's not an unrelevant question, and this is something that's yes. So it would mean that the outer shells were expelled, like let's say, I don't know, a few years prior, and then a few months prior to the actual explosion, there's this confined CSM, which is
right,
which shows, and then then it's a normal supernovae, and then it's again an interaction supernovae. So
Cool.
The classification of supernovae is like, I think it's evolving.
Indeed.
With everything that we're finding, there's a lot of things to reconsider, I think.
Indeed. Life was simpler when there was only 1 and 2, and now there's, there's a whole zoology of these things. That's great. Great.
Is there hydrogen or not? No? Okay, great. It's a 1A.
Absolutely. Absolutely. Very cool.
Sorry, that's one last thing I wanted. Sorry, now I'm seeing it in
Yeah, we should.
This is, so I'm not really making a focus on this because I don't think we have enough data with this sample to really answer this question, which is there a difference in photometry at early time between flashers and non-flashers? Which is one of the questions that my PhD is sort of trying to focus on.
Yes.
Because in the previous papers, it was said that clearly flashers are brighter than non-flashers, but this sample is showing that not really. Within error bars, not really. They're pretty similar. There's maybe the LEH, which is a very bright one in green band, but it was classified as a twin, so it's it's a bright one intrinsically, but otherwise no, there is no clear difference, but it's to be continued, because I don't think it's I mean, it's an interesting question, and it should be investigated more.
Okay. Very cool. Very cool. All right. Well, Rachel, thank you very much for walking us through this very lovely article. And you hinted at it a little bit, so let me go ahead and ask, where do we go over the next, let's say, 5 years? Are there new telescopes coming online that could help address this question? Yeah, just where do we go from here to help answer this?
So I'll be honest that I don't have all the keys in hand to understand exactly what is coming up or not, but there are a few things. First of all, like there's the phase 2 of ZTF, which is still giving a pretty nice cadence. There is LSST, which is coming up soon, but from my latest understanding, it is aimed at going deep and not necessarily with very deep, deeper than ZTF.
Okay.
But not necessarily at a cadence of like several observations per night, okay. which like to find one of our goal would be to find a supernova exploding within hours, like 1 or 2 hours from explosion. And in these cases, I think that for this type of science, it won't be as performant. Mm-hmm. However, this is the last information I've had, so maybe I'm not updated. But it's going to be like, obviously data from these big surveys are going to be very useful. And on top of it, what is nice is that LSST is supposed to be in the south, which can work in synergy with the upcoming SOX, which is a spectrograph dedicated for transient science on the MIT. Well, it's upcoming. COVID allows, and having this type of synergies is incredible, because one of the limiting factor in looking at early time in spectroscopy is having like easily accessible as spectrographs and spectroscopic facilities, which one can respond in less than a few hours, two have a good enough quality and and by quality I mean signal to noise and resolution, and it's like this is one of the cases that we have with the SCDM. SCDM is nice, but SCDM has a low resolution, and sometimes it's not enough to really discriminate between flasher and non-flasher. And with SOX, it would be perfect. It would be amazing and very great quality of data that we would get, and very quickly, because it's dedicated for, it should be dedicated for this. So with LSST, there's a good synergy. This is one of the conclusions I've had. But other than the next telescopes which are coming online, there's also there was already a lot of like really interesting supernovae which were discovered by ZTF and are waiting to be analyzed. So this is a little bit the upcoming, like an extension of this paper, and also maybe having more mysteries to and surprise to talk about in future papers, and they're upcoming, working on it.
Well, I think it's very vibrant. What you described there is very vibrant. So I anticipate you're going to have a bright future over the next couple of years, analyzing some of this data and trying to get to the bottom of how many of these things do an ejection prior to core collapse. So very nice, very nice.
Very exciting.
Yeah, it is. It's great. Very nice. Rachel, I want to thank you once again for walking us through your very lovely APJ paper.
Thank you.
And thank you, everyone. And we will see you on the next one. Bye-bye.
Bye.